All right, this is the third video on comparing means. And like I said, we're going to look at confidence intervals and how those compare to hypothesis tests in this video. But first, we want to go very quickly over the assumptions that we have to make whenever we do a two-sample t-test. So here are the three assumptions of a two-sample t-test. Let's go through these one at a time. First of all, we assume that the observations are independent. This is a little bit complicated to explain, and we're not going to go into a lot of detail in this class. In general, we're not going to go into a lot of detail talking about assumptions in this class, but I do want to briefly let you know about what kinds of things we're talking about when we make assumptions to create a p-value in a hypothesis test. So the basic way we can think about independence of observations is that we're saying that there's some sort of true randomness that's entering into our process. Maybe we have a simple random sample. Maybe we have a random treatment where we've done a randomized control trial. We randomly select cars and based on flipping a coin or some other random process, we decide to either give them the fuel additive or not. As long as we've done something like that, we should generally have meet this assumption and have independence of observations. One way we could violate the independence of observations is if we're maybe looking at clusters where a bunch of observations are all interrelated to one another. So, for example, if I'm looking at education data and I have a bunch of observations that are all coming from different students in the same classroom, because all of those students are probably being exposed to a lot of the same things, they have the same teacher, for example, their values aren't going to be independent from one another. And so we're going to violate this first assumption if we have clustering, we would call it, like a bunch of students coming from the same classroom. All right, what about this second assumption? The variable of interest is normally distributed in the population. In this case, we would say that gas mileage is normally distributed in the population. So formally, we have to make this assumption to be able to do the t-test, but it turns out that the t-test usually works pretty well, even if we don't actually meet this assumption, as long as we have a large sample. And that's the reason that's the case is because of the central limit theorem, which we haven't talked about in a lot of detail in this class, but you can read about it a bit in the textbook if you're curious. Basically, as when we say a large sample, we mean something like 30 observations or more. As long as we have a lot of observations, we should be fine using a two-sample t-test, even if we violate the second assumption. Of course, in our example that we just went through, we didn't have a full 30 observations. So that we might want to think about, do we actually have a normal distribution if we're using this test with a small sample like we just used it with? All right. The third assumption is that the variance of the two populations are equal. Remember, I said we think about having two hypothetical populations, right? One where all cars receive the fuel additive, one where none of the cars receive the fuel additive. We're assuming that the variance in those two populations are equal. It turns out that if we are worried that we might be violating this assumption, it's actually really easy in Stata to have it compute things slightly differently without making this assumption. So all we have to do is run our t-test command and add the option unequal, I believe is what it's called. And once we do this, you'll see we get a slightly different p-value. This time we got 0.1678 instead of 0.1673. So this only differed in the third digit, but it is a slightly different p-value. And the reason the p-value is slightly different is because we didn't make this third assumption. We used a slightly different procedure that didn't require us to make that third assumption. So if we're worried about violating that third assumption, there's a very easy fix for it. So again, I don't expect you to know these assumptions, but I do think it's useful to see at least one example of what it looks like to make assumptions for a test. Okay, let's talk a little bit about confidence intervals and how they compare to hypothesis testing. So confidence intervals have several similarities to hypothesis tests. Specifically, both confidence intervals and hypothesis tests rely on our standard error estimates. We learned about those a couple lectures ago, and standard errors estimates, again, if you'll remember, they tell us how precise our estimate is. In other words, how much certainty do we have around our estimate? We need to know something about how precise our estimates are to either be able to construct a confidence interval or to do a hypothesis test. So under the hood, even if you don't always pay attention to the standard error, Stata is using a standard error estimate to be able to calculate either a confidence interval or a hypothesis test. Both a confidence interval and a hypothesis test require us to pick an alpha level. When we're talking about confidence intervals, we often talk about the confidence level, which is just the opposite, the other side of the coin of an alpha level. If I have an alpha level of 0.05 or 5%, I have a confidence interval that would be a 95% confidence interval. In other words, we just subtract our alpha level from 1, right? 1 minus 0.05 gives us 0.95, and then we convert 0.95 to a percentage, 95%, to be able to describe it in equal terms for a confidence interval. But we have to pick a confidence level or an alpha level before we can conduct either of these analyses, before we can create a confidence interval or create a hypothesis test. Another similarity is that the results of the two approaches are actually interrelated. So there's a way that we can use a confidence interval to actually conduct a hypothesis test. Specifically, if we're doing, at least when we're doing a two-sided hypothesis test, if we have a one-sided hypothesis test, this simple approach doesn't necessarily work. But with a two-sided alternative hypothesis in our hypothesis test, we can figure out what the results from the hypothesis test would be just by looking at our confidence interval and seeing whether or not the value specified in our null hypothesis falls within the confidence interval. Now, to be a little bit more specific, we have to think about what our null hypothesis is. So in the example before, we said that the mean of the two populations are equal, or in other words, the difference between the two populations was equal to 0. Well, if we create a confidence interval for the difference between those means, we can see whether or not 0 is within that confidence interval, and that's how we can figure out what the results from the hypothesis test would be using a confidence interval. The opposite is also true. If 0 falls outside of that confidence interval, or whatever parameter value we're testing in our null hypothesis, if it falls outside the range of the confidence interval, then we're going to reject the null hypothesis. So in Stata, like we said a bit ago in the prior video, Stata output for t-tests is also going to give us confidence intervals, and most or at least many procedures that we run in Stata, it's automatically going to give us both a p-value for a hypothesis test and a confidence interval. Specifically, in the example that we just had, the confidence interval that we're going to need to focus on if we want to be able to see this relationship that we just talked about, where the confidence interval can be used to figure out what the results of the hypothesis test will be, we need to focus on the confidence interval that corresponds to the difference between the means of the two populations, which is not the main confidence interval that we focused on before. So let's go back up to our original t-test that we ran. You can see that before we focused on these confidence intervals, the ones that we graphed. But the confidence interval that actually corresponds to our hypothesis test is this confidence interval right here, because this is the confidence interval that's telling us what do we think the difference between the mean and the two populations is. We're something like 95% confident that, or at least if we used this procedure to create a confidence interval, 95% of the time it would be true that this interval contains the true difference between the means of the population. Now, what I noticed about this confidence interval right away, it's a 95% confidence interval. What I noticed about it right away is that 0 falls within this range, because 0 is both greater than negative 4.3 and less than 0.8. Since 0 falls within this confidence interval, then that means it's very plausible that the difference between the two means is equal to 0. Which is very similar to saying that our results are not statistically significant, or that we fail to reject the null hypothesis, because we can't conclude that the difference is non-zero. It's plausible based on these results that the difference between the two populations could be zero. In other words, it's plausible that the fuel additive has no effect on our results, or no effect on gas mileage. All right. Let's talk just a little bit more about confidence intervals. Hypothesis testing is probably the dominant interpretive tool that we see in applied social science. So if you're reading academic articles, you're probably more likely to see people talking about statistically significant results, which refer to hypothesis tests, than you are to hear them talk about confidence intervals. If you read journalism about science, you're often going to hear them talk about statistical significance, probably more so than confidence intervals. So hypothesis testing really is a dominant tool. However, hypothesis testing has actually received some criticism because it turns out the confidence intervals generally give us more information. Part of the reason for this is that a hypothesis test only allows us to either confirm that there's a non-zero effect or fail to confirm that. But it could be that the effect is so tiny that we don't care. So this usually is a concern when we have a really, really large sample. It could be that we could confirm that, yes, the difference between these two populations, the ones that didn't get the fuel additive, the ones that got the fuel additive, is non-zero, that there's some difference between those two groups. In other words, the fuel additive has some effect. All the hypothesis test allows us to do is ask the question, does the fuel additive have some effect, some non-zero effect? But it might be that if we have a really, really large sample, we find that it's a non-zero effect, but maybe the fuel additive only improves fuel efficiency by 0.005 miles per gallon. We'd have to have a really big sample in order for a difference that small to be statistically significant, to indicate that it is a non-zero effect. But that effect would be so small that we would never care about it. The fuel additive wouldn't do us any good if it only improved gas mileage by 0.005 miles per gallon. Nobody would be willing to pay for that fuel additive. So especially when we have big samples, this can be a concern. And sometimes we do have really huge data sets. And so we do run into this problem where we might find something that's statistically significant, but it's a tiny, tiny difference or a tiny, tiny effect that we don't really care about. With confidence intervals focus our attention on a range of plausible values for what that difference or that effect would be, which is part of the reason that confidence intervals are more informative. They allow us to answer the question, how big is the difference or how big is the effect, which a hypothesis test doesn't really let us do, at least as hypothesis tests are normally constructed. Similarly, if a hypothesis test gives us insignificant results, if we fail to confirm the null or fail to reject the null hypothesis, that tells us very little. Again, I apologize for the mistakes on these slides. This should be fail to reject the null, not fail to confirm. If we fail to reject the null hypothesis, we learn virtually nothing because we don't know why we failed to reject the null hypothesis. It could be that we just had a really tiny sample, so we weren't able to bring much evidence to the table regarding whether or not the null hypothesis might be true. With a confidence interval, we get a range of possible values or plausible values. And so we can easily say, either, oh, I have a really, really wide confidence interval. I can't conclude much. Maybe I need to go collect more data. Or I could say, I have a really narrow confidence interval, and it just happens to include zero, which lets, in other words, my data is telling me that the effect of this treatment was something close to zero. Maybe not exactly zero, but something close to zero. In other words, it was a very, very small or non-zero effect. That's part of the reason that people sometimes think that confidence intervals are more useful. These issues will come up prominently in the context of regression, which we'll talk about more in later lectures in this course. All right, that's almost all we've got for this part of the lecture. Let me say just a couple more words about confidence intervals. We've mainly focused on 95% confidence intervals so far in this class. But as I mentioned, anytime we create a confidence interval, we have to pick an alpha level. And generally, the default alpha level is 0.05, which means generally the default confidence level is 95%. But Stata actually allows us to compute confidence intervals for other alpha levels. So let's look at an example of that in just a moment. The way that Stata is going to do this in the background is that it's going to find what's called a critical value using, for example, the t-distribution. And whatever distribution it's using, usually often the t-distribution, the example we're going to see is the t-distribution, it's picking that value to multiply the standard error by, such that the probability of drawing a value from the distribution that we've assumed, for example, the t-distribution, drawing a value from that distribution that is further from the mean than the critical value is equal to our alpha level. In other words, if we have an alpha level of 0.1, then 10% of the time we'll get something that's outside of that value. Conversely, the confidence level is 90%. So that means that 90% of the time we're going to get a value that is within that range. So here's the formula that Stata is using, where they implement that critical value being multiplied by the standard error, and then using the estimate, in this case the sample mean, and adding or subtracting this part of the expression to the estimate. That's how it's going to create a confidence interval. And this is a formula that can be used for any confidence level. It's just that the value of t star, the critical value of t, is going to change depending on what confidence level we've selected. So let's look at a quick example in Stata. This is still using the same data set, but I want to think about just the observations where they did not receive the fuel additive. So in other words, what is the typical gas mileage among cars just ordinarily without receiving this fuel additive? So I'm going to use this command, which is just going to drop the 12 observations that received the fuel, where the fuel additive was received. You can see this is what my data set looks like now. And now I've got a couple of different expressions that I'm going to run here. So the first one is just the ordinary 95% confidence interval that you've seen before. So let's see what happens when I run this. It tells me that my mean is 21, which we already knew from our prior analysis. And this is our confidence interval, which should look just like the confidence interval that we got up here. In other words, we're 95% confident that the true mean gas mileage for our population is somewhere between about 19 and 23 miles per gallon. That's a rough interpretation of the confidence interval. This is using 95% confidence. Well, what if I want to do 90% confidence? Stata lets us just change the number that we put inside this option called level to be able to get a different confidence level. And most Stata commands will have a way for you to change what the confidence level is. Now you can see we're looking at a 90% confidence interval. And you can see that the confidence interval has gotten slightly narrower. In other words, we're saying we're more willing to be wrong, right? We're going to let 10% of the time the truth fall outside of our window, instead of only letting it fall outside our window 5% of the time. In other words, 10% of the time we're willing to be wrong instead of 5% of the time. Since we're willing to be wrong 10% of the time, we're only looking for 90% confidence that we're right, we get a narrower range, right? We're able to say something a little bit more precise. And so you can see that now we would say something like, I'm 90% confident that the truth is between about 20 and about 22 if we just round to 0 decimal places. All right, that finishes up our discussion of confidence intervals for this lecture. In the next and final video for this lecture, we're going to discuss ANOVA, which is going to let us compare means across more than 2 groups, if we have 3 or 4 groups, for example.